Hello. Welcome and thank you for attending my talk. My name is Sean Mullan. I work for Oracle and I am the OpenJDK Security Group Lead. Today I'm going to talk about Java and PQC, or Post-Quantum Cryptography. So does everyone know what this is a photo of? Just a raise of hands. Okay, most of you. So this is a quantum computer, specifically an IBM Quantum System 1. Someday, it is predicted that a quantum computer much more powerful than the one you see in this photo will be able to break all traditional public key-based cryptography, also called asymmetric cryptography. And that's used to secure much of the data on the internet today. Today, I'm going to show you how we're enhancing and adapting the Java platform to protect your applications and data from this future threat. My talk basically consists of two parts. In the first part, I'm going to give an overview of quantum computers and explain why they are a threat. I'll also discuss the various post-quantum algorithms that are being standardized and the challenges in implementing and deploying them. In the second part, I'm going to discuss the PQC enhancements that we have already made to the Java platform. So my aim today is to show you that Java is ready for quantum computers. They labeled this talk as an expert talk, but I think it's more like an intermediate level. I will be showing some code, so if you're a developer, you'll probably like that. But if you're an end user, an administrator, or simply want to know more about PQC and Java, I think you'll find the information in my talk useful. So without further ado, let's get started. Okay, to understand the need for PQC, we first need to understand a little bit about a quantum computer and what makes it different from a traditional computer, which is the computers that you use today, like this. A quantum computer uses qubits, which are different than a traditional computer, which uses bits. A qubit is the basic unit of information in quantum computer. It's similar to a classical bit, but unlike a classical bit, which can only be 0 or 1, a qubit can be in a state of 0 or 1 or a combination of both 0 and 1 at the same time. A good analogy is a coin flip. While the coin is in the air, it may be either heads or tails with certain probabilities. And qubits can also be entangled with one another, meaning the state of one qubit can be related to another, even at like really great distances. And that allows them to be in many states in parallel. So why does this matter? Well, the properties of quantum computers allow quantum algorithms to exploit these effects and solve certain problems much faster than traditional computers. And one of these algorithms, which I'll talk about next, has the potential to break all asymmetric cryptography in use today. Now, it's still early. Quantum computers are still mostly in an experimental state. They've been able to build quantum computers with 100 to 1,000 physical qubits. But there are still a lot of challenges, mostly in the area of error correction and scaling. So these type of problems need to be addressed before a quantum computer can break these cryptographic algorithms. So our story really begins back in 1994. When a brilliant mathematician named Peter Shor invented Shor's algorithm. Shor's algorithm is a quantum computing algorithm that efficiently finds the prime factors of large integers and solves discrete logarithms in polynomial time. This was an incredible discovery because it meant that in theory, Shor's algorithm could break all traditional asymmetric cryptographic algorithms, including RSA, Diffie-Hellman, and its elliptic curve variants. Basically, a problem of exponential complexity was reduced to polynomial complexity. However, Shor's algorithm needs a large-scale quantum computer to break these crypto algorithms. In 1994, a quantum computer didn't even exist yet. It wasn't until later, when experimental systems started to be created, that people started to get a little bit concerned. But real cryptographic impact is not expected until a quantum computer can be built with millions of physical qubits. Experts have different opinions, but many predict that a cryptographically relevant quantum computer, also called a CRQC, could be created within the next 10 to 20 years. Some think it might be earlier, others think it might be later than that. On the right is a photo of Peter Shor at the International Center of Theoretical Physics in Italy, where he was awarded the Dirac Medal in 2017 for his work in quantum computing. So what is important to know is that a CRQC will break all internet communications that use traditional asymmetric cryptography. So most secure communication on the internet today uses TLS, or transport layer security. And TLS uses three primary cryptographic primitives to secure your session. The first is key exchange, which establishes a shared session key between two parties, typically a client or server. Digital signatures provide authentication so that you are assured that you're talking to the server that you think you should be talking to, or vice versa. And finally, symmetric encryption uses the key that was established during the key exchange phase to encrypt data over the insecure internet channel. The diagram on the right is a simplified version of the TLS 1.3 handshake, showing which parts are the key exchange and which parts are the authentication. Now, both key exchange and digital signatures are based on asymmetric cryptography, so they're both vulnerable to Shor's algorithm. So if, and more likely when, a CRQC is created, the results would be devastating to the secure communications on the internet. Signatures could be forged, allowing man-in-the-middle attacks. Secrets protected by key exchange would be cracked, allowing sessions to be decrypted. And this would affect so many critical applications used on the internet today, from commerce, social networks, cloud computing, and more. So even though most people believe a CRQC won't be developed for, maybe 10, 20 years, unfortunately, there is an issue called harvest-now-decrypt-later, also called store-now-decrypt-later. And that's pushing the industry to implement and deploy protections against quantum computers sooner rather than later. So in HNDL, the attack is on the key exchange phase, and it's more serious than the digital signatures. With this type of attack, an adversary can harvest and store key exchange messages and encrypted communication data that passes through networks that it has access to. And even though they can't decrypt it now, they can store it for as long as it takes until a CRQC is developed and becomes available to them. They can then crack the session key and decrypt the contents, thus getting access to all past data communications. Now, you might think a lot of data that is sent today might not be very sensitive years from now, but there could be certain types of data, for example, government-related data, that could be very sensitive years from now. So therefore, deployment of post-quantum key exchange algorithms is considered more urgent than digital signature algorithms. The solutions to these threats is called post-quantum cryptography, or PQC. So interest in post-quantum cryptography slowly gained momentum after Shor's algorithm was discovered. Although no one knew when a CRQC would be created, there was recognition that it would take many years to create and deploy new algorithms that were resistant to quantum computer attacks. Also, there had been considerable progress in the development of quantum computers. Thus, a sense of urgency materialized, and NIST recognized they could play a unique role in this standardization process, as they had with other algorithms, such as AES. NIST stands for the National Institute of Standards and Technology and is part of the US Department of Commerce. So this timeline shows the major events in the standardization of PQC algorithms by NIST. In December 2016, NIST initiated a formal call for proposals for post-quantum key exchange and digital signature algorithms. These algorithms needed to be resistant not only against quantum computers, but also traditional computers, because they're still used today. So NIST expected this process to take several years and several rounds, where fewer and fewer candidates would progress to each round. In December 2017, NIST announced that 69 algorithms had been accepted for round one. In January 2019, NIST announced that 26 of those 69 algorithms had been accepted for round 2. And in July 2020, NIST announced that 7 algorithms had been accepted as finalists for round 3, with 8 alternates, some of those potentially going into a 4th round. And then finally, in July 2022, NIST announced that 4 algorithms were to be standardized, with 4 others going into a round 4. The algorithms that were standardized were Kyber, which is a key encapsulation algorithm based on lattices, Dilithium, a digital signature algorithm also based on lattices, Sphinx, a digital signature algorithm based on hashes, and Falcon, a digital signature algorithm also based on lattices. In August 2023, the FIPS drafts, 3 FIPS drafts were published. Kyber was renamed as ML-KEM, Dilithium was renamed as ML-DSA, and Sphinx was renamed as SLH-DSA. And then finally, in August 2004, those FIPS drafts were published. ML-KEM is FIPS 203, ML-DSA is FIPS 204, and SLH-DSA is FIPS 205. Falcon is still being standardized, and it's going to be published as FN-DSA and FIPS 206. And then more recently, in March 2025, HQC was selected for standardization. That stands for the Hamming forget the name. It's Hamming quasi-cyclic algorithm, and it's a code-based KEM algorithm which uses different math than ML-KEM. So I also want to talk a little bit about hybrid post-quantum schemes, because as you will see later in my talk, that's what we have implemented in our TLS 1.3 implementation for post-quantum key exchange. So some organizations are not yet ready to fully trust these new post-quantum algorithms. Their concern is that many post-quantum algorithms are relatively new and not been in deployment for a long time yet, so they're not battle tested. This is actually a unique situation in which neither the traditional nor the post-quantum algorithms are fully trusted, yet neither of them are broken yet. So a hybrid scheme combines traditional and post-quantum algorithms and is secure as long as one of them remains unbroken. Now, there may be some disadvantages to using a hybrid scheme. Instead of just the post-quantum algorithm on its own, they may consume more CPU or cause more traffic due to increased signature or ciphertext size. But there are a large number of users that want to use hybrids, at least in the near term, until the post-quantum algorithms have undergone more scrutiny. NIST has decided not to standardize hybrid schemes, but the IETF is standardizing them for key exchange and digital signatures. Okay, so PQC is considered a revolutionary change in cryptography and security technology. However, evolving Java security and transitioning to new crypto algorithms is something that our Java security group is already very experienced in. Change is a constant in the security area. No cryptographic algorithm or protocol remains secure forever. Old algorithms are continuously being broken and replaced with stronger ones. To show you what I mean, let me tell you a little bit of a story. I started working on Java security in 2000, and yeah, I know that was a long time ago, but at the time, JDK 1.3 was the latest release. TLS 1.0 was the latest TLS release, and triple-DES, SHA-1, and 1024-bit RSA keys were still in use and considered secure. Fast forward to 2026, JDK 26 is the latest release. TLS 1.3 is the latest TLS version. So there were not 1, not 2, but 3 TLS versions in that time span. TLS 1.0 and 1.1 are both obsolete and not recommended for use anymore. Triple-DES, SHA-1, and 1024-bit RSA keys are considered weak and should not be used anymore. And many other algorithms have since weakened and been deprecated and replaced with stronger alternatives over those years. So my point is that we can't stand still. We always have to move forward. And one of the things I encourage you to track progress on is called the Java Cryptographic Roadmap. That's where we publish changes to the security algorithms of JDK update releases. We want every update release to be secure enough for you to develop secure applications. So you'll find different changes on there, whether it is disabling a weak algorithm, making default key sizes stronger. These are all actions that you should be aware of so that your applications can prepare for and migrate to these stronger security settings. Now, having said that, even though we have a lot of experience continuously phasing out old algorithms and implementing stronger ones, PQC does present a number of significant and somewhat unique challenges. The first challenge is that there are many new PQC algorithms and mechanisms that need to be implemented. And they're based on very different mathematical concepts than traditional asymmetric algorithms. And they have to be resistant to both quantum and traditional computer attacks. PQC also uses new modern schemes such as key encapsulation mechanisms. And in the case of Java, that required us to create new APIs. And as discussed before, PQC is unique in that neither the traditional nor the post-quantum algorithms are fully trusted, making hybrid schemes a popular alternative. Then there's performance and security trade-offs. So many of the PQC algorithms use more CPU or have increased key ciphertext and signature sizes. Finding different ways to balance these performance and security trade-offs is an ongoing and challenging task. And finally, the sheer breadth of technology that needs to be upgraded and replaced can be daunting. I don't think we have ever seen this amount of security technology that needs to be replaced. All uses of asymmetric crypto in general need to be replaced, and that can be a challenging task for software and hardware that has already been deployed for many years. Identifying those uses, replacing and upgrading software and hardware, configuring, administrating, auditing, all take time. But that is why we have started the PQC journey early in the Java platform, to give you enough time to transition. So in the next section of my talk, I'm going to go over the PQC enhancements that we have already made to the Java platform. So I first want to talk about our overall roadmap strategy for implementing PQC in the Java platform. Our initial focus is on building a strong foundation by implementing the core cryptographic PQC algorithms that have been standardized. This includes ML-KEM, ML-DSA, and HSS-LMS, each of which I'll go into more detail later. We also want to add new APIs as needed. For example, we introduced 2 new APIs in the last few JDK releases, KEM and KDF. Next, we want to build on this PQC foundation by adding support in higher layers, such as PKI and TLS. This includes support for features such as jars signed with post-quantum signature algorithms and post-quantum key exchange algorithms for TLS 1.3. We always want to support the standards that are published by NIST and IETF. There's a couple of really important reasons for that. One is that we want to make sure they've been widely reviewed by the security community. And the second one is that we want to make sure that Java can properly interoperate with other implementations that also support those standards. And as mentioned before, many of the PQC algorithms have increased size or processing requirements, so performance is a chief concern. The good news, though, is that we have implemented intrinsics for many of these new algorithms, and our performance is on par or better than other PQC implementations. And finally, this is an ongoing effort that we expect to take several years, and we will continue to add more features, some of which I will touch on near the end of my talk. Okay, so if you're familiar with the Java cryptography architecture, this diagram may look familiar to you. At the top, we have our application, and the application calls the standard JCA or JCE APIs, which represent different cryptographic primitives such as signature and message digest. These APIs are implemented for various algorithms in service providers. The providers may be implemented in Java, in native code, or they may use hardware instructions. So building this core cryptographic foundation for PQC was our initial primary focus. I'll go through some of these in more detail, but from the diagram I can point out that we have added 2 new APIs, KEM and KDF with the new labels, and we have implemented various algorithms. Some of them are post-quantum, such as ML-KEM and ML-DSA, and others are not necessarily post-quantum, but ones that we needed to implement in order to support other PQC algorithms or mechanisms. So the very first PQC feature we added to the JDK was in JDK 21, and it was support for the Leighton-Macaulay signature algorithm, also called HSS LMS. LMS is a stateful hash-based signature algorithm defined in RFC 8554, and it is believed that it will not be broken by a CRQC. Now, LMS requires that the signer maintain state. It's a one-time signature system. So once a particular value of the one-time signature private key is used to sign one message, it must not be used to sign another. Due to these complexities, LMS is not considered a suitable replacement for all use cases of traditional signature algorithms like RSA or ECDSA. However, applications that expect a long lifetime of signature, like firmware or software updates, or even signed jars that have a very long life, are more typical use cases where LMS can be successfully applied. In JDK 21, we added new HSS LMS key factory and signature implementations. However, key factory only supports public keys and signature only supports verification. If you want to support signing or private keys, you need to use a third-party JC provider that provides that support, that stateful signing support that is very important. And in JDK 22, we built on this support and enhanced our tools to support LMS. Jar Signer supports verifying jars with HSS LMS. Signing is also supported, but again, you need to use a third-party JC provider. And KeyTool supports generating LMS key pairs, but again, with a third-party provider. Also in JDK 21, we added a new API for KEM, and that's described more in JEP 452. KEM stands for Key Encapsulation Mechanism. And it's a modern cryptographic technique for securing symmetric keys with asymmetric cryptography. It's considered more secure than the traditional technique that encrypts a randomly generated symmetric key with a public key and requires padding, which has been the source of many security issues over the years. A KEM instead uses properties of the public key to derive a symmetric key, and that requires no padding. So KEMs are now the modern technique for securely exchanging symmetric key material over an insecure channel. They're used in TLS 1.3 hybrid key exchange, which I'll talk about later, and also in hybrid public key encryption, which we've just delivered in JDK 26. When we were designing KEM, we did consider whether existing APIs such as key agreement, key generator, or cipher were sufficient to represent a KEM, but each of them had major disadvantages, and that's discussed more in the alternative section of JEP 452. So we created a new API. The 2 main classes are KEM Encapsulator and KEM Decapsulator. Later, I'll show you an example of how to use this API with the post-quantum ML-KEM algorithm. And the good news is that the API has been backported to JDK 17 as part of the Java SE maintenance release 1. So a few releases later in JDK 24, we added support for ML-KEM. As mentioned earlier, ML-KEM is a quantum-resistant, lattice-based key encapsulation mechanism specified in FIPS 203. It was defined for the Java platform in JEP 496. For ML-KEM, we include new key pair generator, key factory, and KEM implementations. The KEM implementation is based on the KEM API that was introduced in JDK 21. And we support 3 parameter sets in increasing security strength: ML-KEM 512, ML-KEM 768, and ML-KEM 1024. We've also added support to KeyTool so that you can generate ML-KEM key pairs and certificates. Now, since ML-KEM itself is not a signature algorithm, the certificates must be signed with a different algorithm, a signature algorithm. So, for example, you could use RSA or ML-DSA. And we also have plans to backport ML-KEM to Oracle's JDK 21 and 17 update releases in the second half of this year. And that is published on the Java Cryptographic roadmap. So now let's look at an example which uses ML-KEM and the new KEM API to establish a shared secret between a client and server. So first, the client uses a key pair generator to generate an ML-KEM key pair. This generates an ML-KEM key pair with the ML-KEM 768 parameter set by default. The client then sends its public key, which is also called the encapsulation key, to the server. This part is not shown, but in a TLS 1.3 handshake, this would be sent in the key share extension of the client hello message. On the server side, after the server receives the client's encapsulation key, it then instantiates a KEM object for the ML-KEM algorithm. It creates an encapsulator object using the client's encapsulation key, and then calls the encapsulate method, which returns an encapsulated object. From this object, it gets the shared secret key and a ciphertext, also called a key encapsulation message. The server sends the key encapsulation message to the client, and in TLS 1.3, this would be sent in the key share extension of the server hello message. Back on the client side, it receives this key encapsulation message from the server and uses ML-KEM to decapsulate it with its private key and gets the same shared secret as the server. And so now they can begin encrypted communications with one another. So JDK 24 was a pretty significant release for us. We also added support for ML-DSA. As mentioned earlier, ML-DSA is a quantum-resistant, lattice-based signature algorithm standardized by NIST in FIPS 204. And for the Java platform, it was defined in JEP 497. For ML-DSA, we added new key pair generator, key factory, and signature implementations. But we did not have to add any new APIs. ML-DSA fits very well within our APIs, just like other algorithms such as RSA. We support 3 parameter sets and increasing security strengths: ML-DSA 44, ML-DSA 65, and ML-DSA 87. And you can also use KeyTool to create ML-DSA key pairs and certificates. The generated key pairs use the ML-DSA 65 parameter set by default, unless you specify a specific parameter set. And also, as of JDK 26, jar signer now supports signing and verifying jars signed with ML-DSA. And just like ML-KEM, we have plans to backport ML-DSA to Oracle's JDK 17 and 21 releases in the second half of this year. And that's also published on the Java Cryptographic roadmap. So I want to show you an example of using KeyTool now to generate ML-KEM and ML-DSA key pairs and certificates. So in the first command line, we use KeyTool to create an ML-DSA key pair and self-signed certificate with the ML-DSA 65 parameter set. As mentioned before, ML-DSA 65 is the default parameter set used by KeyTool if you don't specify the -group name option. But I'm showing it here just to illustrate how to specify a specific parameter set. We specify a distinguished name with the -d name option and the -ext option with a value of BC, which stands for the basic constraints extension. And it means that the certificate that is created will be a CA, or a certificate authority certificate. When we run this command, the key pair and certificate are stored in a key store named KS with an alias name of ML-DSA. Next, we're going to use KeyTool to create an ML-KEM key pair with the ML-KEM 768 parameter set. Again, that's the default parameter set if you don't specify the group name option. And again, as I mentioned, for this example, because ML-KEM is not a digital signature algorithm, we need to specify a signer alias with the signer option, and that signer's private key will be used to sign the certificate containing the ML-KEM public key. So here we can simply specify the alias of the ML-DSA key pair we created in the previous command, and we run this command, and KeyTool creates an ML-KEM key pair and a certificate signed with ML-DSA. Now let's look at an example of using jar signer to sign and verify jars with ML-DSA. This example builds on the prior example and uses the key pair and certificate we created. So first we use jar signer to sign a jar named test.jar with the ML-DSA signature algorithm. We specify that we want to use the ML-DSA 65 parameter set with the -sigalg option. And we specify the KS key store and the ML-DSA key store alias containing the ML-DSA private key that we did create earlier in the previous slide. When we run this command, jar signer signs test.jar with ML-DSA and stores it in the file named sign.jar. It does print a warning that the signer certificate is self-signed, but this is just for demonstration, so that's okay. To verify the jar, we use jar signer again, but this time we specify the -verify and -verbose options. This prints the contents of the jar, who signed it, the digest and signature algorithms, and a message that the jar was successfully verified. There are a couple warnings at the end about the self-signed certificate again and a few other recommendations for you, but I had removed them due to space constraints. Okay, I want to talk about the other main API that we introduced in the last few releases. So in JDK 24, we introduced a preview API for key derivation functions, or KDF. KDF is a cryptographic algorithm for deriving additional keys from a secret key and other data. It was initially previewed in JDK 24 and JEP 478, and then finalized in JDK 25 in JEP 510. It includes an implementation of HKDF, which stands for the HMAC-based extract and expand key derivation function. And HKDF is specified in RFC 5869. Now, we did initially consider, again, we looked at our existing APIs such as secret key factory and key generator, but in the end, we decided they weren't really sufficient to represent a KDF. And that's more of those disadvantages are discussed in the JEP. So the primary new API is KDF, and there is also a class for service providers called KDF SPI. And HKDF parameter spec is an API which you use to specify input parameters for the HKDF algorithm.
Excuse me. Can you clarify what
the initial key material? I'll show you an example. Next slide. So KDF has become an essential component for deriving keys and is used in modern schemes and protocols such as hybrid public key encryption and TLS 1.3, including hybrid key exchange. And we also have future plans to implement the Argon 2 password hashing algorithm. That was the winner of the 2015 password hashing competition, and we have plans to implement that as a KDF implementation. So I'm going to show you an example of using HKDF and the KDF API. Maybe this will answer your question. Although this is not specifically a post-quantum algorithm, I think it is still useful to show you how the API can be used. So we first instantiate a KDF object with the algorithm that we want to use, in this case, HKDF SHA-384. We then create a builder for the parameters of the extract option. We created a builder because there are a lot of parameters, so it's easier to use it using the builder API. Then we add initial key material, which could be the result of a KEM encapsulation operation. We could use that as the initial key material to derive more keys. And we also add some salt for security reasons. We then call the then-expand method of the builder, and that creates an extract then expand object containing the parameters that we're going to input into the KDF. Oh, In the previous call, to then expand, we specified two parameters, an optional information bytes, just used for informational purposes, and also the size of the keys that we want to derive. In this case, we want to derive 32-byte keys. And then when we call the derive key method on the HKDF object that we created in the first step, we tell it what type of keys we want. In this case, we want an AES key, and we pass it the parameters that we created earlier. And that returns a 32-byte AES symmetric key. Okay, I have a couple more important features to go over. In JDK 26, which just came out on Tuesday, we added support for hybrid public key encryption, or HPKE. HPKE is a modern encryption scheme for encrypting arbitrary-sized plain texts with a recipient's public key, and it's defined in RFC 9180. It combines three different algorithms, a KEM, a KDF, and an AEAD algorithm to produce a ciphertext. So it builds on a lot of the support that we already added in previous releases. The good news is that to use HPKE in your applications, you can use the existing Cipher API and a new HPKE parameter spec class, which basically specifies the three algorithms that you want to use, KEM, KDF, and AEAD. Initially in JDK 26, we only support traditional non-PQC algorithms. However, we plan to add support for PQC algorithms in a later JDK release once the IETF draft that's making its way through the IETF becomes a RFC. Okay, I think I could probably bet that I've saved our best and probably most sought after PQC feature for the end. I'm very happy to announce that we'll be adding support for post-quantum hybrid key exchange for TLS 1.3 in JDK 27, and that'll be released later this year. So this is a significant feature that adds PQC support to TLS 1.3 and builds on many of the features that I previously discussed. This feature combines classical or traditional and post-quantum key exchange algorithms in a hybrid approach and protects against the harvest-now-decrypt-later risk, which I talked about earlier. So just to review, a hybrid scheme combines both a traditional and a post-quantum algorithm, and it's secure as long as one of those algorithms remains unbroken. We've added support for the three hybrid groups that have been defined by the IETF: X25519 ML-KEM 768, SecP256 R1 ML-KEM 768, and SecP384 R1 ML-KEM 1024. These combine the quantum-resistant ML-KEM algorithm with traditional elliptic curve algorithms. And the good news is that this feature has already been integrated into JDK 27. So if you want to try it out now before it's released, I encourage you to download one of those EA builds and let us know what you think. So you might be asking, okay, what do I have to do to my Java applications that use TLS in order to take advantage of this new feature? The answer is nothing. We've specifically designed this feature such that by default it works out of the box, requires no new APIs, no new code, no configuration changes. By default, the X25519 ML-KEM 768 hybrid key exchange group is enabled by default. As long as your peer, and if it's JDK 27, it does, as long as your peer also supports that group and honors our group preference order, then your session should be protected and quantum resistant. The X25519 ML-KEM 768 hybrid group is the most common group supported by other TLS implementations that also support post-quantum hybrid key exchange. The only case where you may have to make changes is if your application wants to use one of those other hybrid groups that I mentioned earlier, or they're not using the default name groups for some reason. And the JEP shows a couple of examples how to do that, one by using the SSL parameters set name groups API, and the other way is to use the JDK TLS name groups system property. Okay, so this diagram is a summary of our PQC support in the Java platform as of JDK 27. The bottom layer shows the two new APIs we have added, KEM in JDK 21 and KDF in JDK 25. The middle layer shows the algorithms that we've implemented, HSS LMS in JDK 21, ML-KEM and ML-DSA in JDK 24, and HKDF in JDK 25. Of course, as I mentioned before, HKDF is not itself a post-quantum algorithm, but it's used by other PQC features, and so it's part of our overall PQC story. And as the top layer is the application layer. These features depend on the algorithms and APIs that we've added in the bottom and middle layers. So we've added support for signed jars with HSS LMS in JDK 21 and ML-DSA in JDK 26. We've added support for HPKE in JDK 26, and we're adding support for post-quantum hybrid key exchange for TLS 1.3 in JDK 27. So I hope that I've achieved my goal today and that you agree that Java is ready for quantum computers. Before we finish, I would also like to talk briefly about some projects that we were working on for the near future. Not all of these are related to PQC, but given that this is a security talk, I figured you might be interested in them as well. For JDK 27, we have several features and enhancements we're working on. I've marked them tentative as plans could change before 27 is released. First, we plan to deliver the final version of the PEM API, and that's a new API for encoding and decoding security-related objects to and from the widely used PEM format. If you haven't tried it out, I encourage you to try it out. It's in JDK 26, the preview 2, and that's pretty similar to what we're going to be including as the final version. We're also working on an implementation of the Argon 2 password hashing algorithm. This is a memory-hard algorithm, and it provides better protection against brute force password guessing attacks. It will use the new KDF API, and we also have a JEP draft that was just published a week or two ago, and I encourage you to read that and give us feedback. We're working on adding certificate compression to our TLS implementation. This feature reduces the size of certificate chains exchanged during the TLS handshake. And we're also working on enhancing our post-quantum LMS signature implementation to support RFC 9858, and that will add support for additional hash functions. We're working on a couple of JLink plugins, which will allow a user to customize the security configuration of a runtime. The CA certs plugin will allow you to just specify only the root certificates that your application really needs. And the security properties will allow you to selectively override certain security properties. So both of these plugins will allow you to create a more secure runtime for the application according to its needs. PQC is still a very active area. We're continuing to track developments in NIST and IETF, and the most I'll say today is that we will continue to implement features that we believe are important for the security of the Java platform. So just a couple of useful pointers we can go to get more information. The OpenJDK Security Group is where we do all of our development, and the mailing list is where we post JEPs and PRs, and that's our main list for development-related topics. The Security Developers Guide covers all of our components and contains programming examples and other useful information. The Java cryptographic roadmap is important for getting advance notice of security changes, so you can try them out, make sure your application won't be affected, or if it is affected, try to move to the stronger algorithms. And then secure coding guidelines. Drew talked about that earlier this morning. That provides best practices for writing more secure Java code. And finally, I have a Java security blog where I blog about the new security features in each JDK release. And I've just updated that to include JDK 26. Thank you again for attending my talk. Before I open it up for Q&A, I just want to take this opportunity to thank my team for all the hard work it took to get us here, and also my management team for guiding us and helping us to achieve this major milestone. So thank you very much. If you can use the mic, I think it would be most helpful.
All right, thank you for the talk. Maybe a very stupid question, but what makes these algorithms quantum resistant?
Well, that would be a whole nother talk in itself, but lattices, go watch some videos on lattices and quantum cryptography, and that's what most of them are based on. Yeah.
All right, thank you.
Hi, thanks for the talk. Not so much a PQC specific question, but a bit more security kind of best practices question. I understand that in the kind of enterprise environment, it happens so that sometimes engineers, SREs, and so on, opt for a less secure options in properties, and because that makes the application running. Is there a built-into platform mechanism such as maybe MBean that would allow to build dashboards essentially and list insecure instances of applications that are running, like, for example, somebody opted in for TLS 1.0 and running that, and I would like to be able to build a dashboard across like a fleet of machines and applications and be able to flag that.
Oh, yeah. So one of the
the
things we've added to the last few JDK releases is cryptographic events for Java Flight Recorder.
Oh.
So if you run your application with Java Flight Recorder, and some of these events may not be enabled by default, so you might have to enable them, it will show you the TLS protocol that's being used, the cipher suite, and it will tell you the cryptographic algorithms they're using, all the way down to the JCE layer. And so you'll get a very comprehensive view of what's going on.
That's what I was looking for. Thank you.
Hi. So my understanding is that the keys for these new algorithms are like orders of magnitude longer than
Yes.
for traditional
Yes.
algorithms. And especially if you're going to do the hybrid approach, now it's like you've got the new key and the old key, and certificates are going to get really quite large
Yes.
compared to how they used to be.
Yes.
So I guess you briefly mentioned like certificate compression. I don't know exactly how much that helps, but there's also, I know Cloudflare and Google are actively working on Merkle tree certificates
Yes.
to try to solve this problem. Is that something that's being, I mean, I know it's still very early days
Yes.
there, but is that something that's being considered?
Well, first of all, I'll say for the TLS hybrid key exchange, it's not considered that much of a performance issue. It does increase the key size a little bit, but with respect to the whole handshake, it's still considered acceptable. Certificates, yes, that's a problem. I think we are tracking what's going on. It's called the Plants Working Group in the IETF and the Merkle tree certificates. So we're definitely tracking that, and if it makes sense to support it, we probably will.
Okay, but maybe a little early to have it in.
Yeah, it's a little early.
Okay, good.
Hi, I'm a Netty maintainer, and you'll probably be happy to know we already have support for the X25519 ML-KEM key agreement.
Yep.
And I'm just letting you know that we'll be adding JDK 27 early access to our build matrix to ensure compatibility.
Oh, excellent. Where did you say you were from?
Netty.
Netty, okay, Netty, yeah, Project Netty, great, awesome.
Hello, I have two questions. The first one is the Shor algorithms in the only thread, like to the current cryptography? So are there any other, I don't know, ideas or which might break?
Yeah, the other algorithm that you might hear a lot about is Grover's algorithm. And the general advice that you might hear is that AES is safe, but if you want to be, reasonably sure that you're not going to be affected by Grover's algorithm, use AES 256 instead of AES 128. But that's the only other quantum algorithm that I know of right now that is a threat to cryptography.
And the second question, if you already implemented this like post-quantum cryptography, like new algorithm key exchange in TLS, how much performance degradations you see? Because you said that it's more computationally takes more CPU to compute the exchange.
Yeah, I don't have the numbers today, but you know, we're looking at other areas where we can improve performance such that it really is not much of an issue in the end. Yeah.
Thank you.
Hello, you were mentioning that you plan to downport some of these new algorithms to JDK 17 and 21. Does that mean that we need new maintenance releases of the corresponding SE specification?
So for ML-KEM, because it depends on the KEM API, that did require a maintenance release for Java 17. TLS hybrid key exchange, it depends. It doesn't really depend on new APIs, so I can't really say if there'll be a maintenance release or not, but that's all in plans that I don't have any data today to share with you.
Okay, thanks.
Yeah, I think we're over. Thanks, everyone.